Hello YouTube. My name's Juliano. I'm a just graduating undergrad from Arizona State University. I'm a member of the Kristen Swanson Lab, or soon to be member. Some of the stuff that I do, that we're going to be doing in that research lab, is investigating the effect of immune cell populations on glioblastoma, which is one of the most deadly forms of brain cancers. And we're specifically interested in the interaction and how microglia play into tumor progression and tumor genesis. You might think of immune cells as trying to destroy the tumor, but as it turns out, microglia and macrophages has been observed to actually help and aid the progression of tumor, glioblastoma, and in fact other cancers as well. And so my project is specifically interested in investigating that interaction.
What are these microglia? Can you go into some of the terms real quick?
So microglia, it's it's a part of the innate immune system in the brain, and essentially these cells, they can originate from the bone marrow and spread up into the brain, or they are resident, they are there to begin with. But for the context of microglia, we think of them as sort of surveillance of synaptic responses within the brain. We call them the resident immune cell population. They also do a lot of things like calling other immune cell populations to the site of injury, T cells, and so these are also they signal other immune cells to come in and attack certain conditions that are affecting the brain.
So how does math play a role?
Well, the cool thing about math is you can add math and implement math into almost any kind of research. And whether you see it involved in, as this is my phone. So this is probably breaking up your footage totally.
Yeah, it's all good.
Math plays a role in almost any kind of research project. And so traditionally you see it, and many high school students go through mathematics looking at mostly engineering and physics problems. One of the cool things is that as you get more into math, past calculus, there's so many different biology applications that it can be involved in. And so one of the things that we do is, first of all, we use math to be able to model how tumors progress and where they may spread. And so we're actually, just like you might be forecasting the weather using math models, we're trying to forecast tumor growth. In terms of my project, I'm trying to use math to actually model how these cells move. So if we can come up with a model of how microglia are moving in the context of a tumor, or how they may be moving in the context outside the tumor, we're trying to determine whether that movement description can actually describe how these cells, the function that these cells have with regards to aiding progression of tumors, or trying to kill off tumors.
How can this actually help clinical stuff? How could doctors benefit from this?
Well, there's immediate benefits that we get when we're trying to simulate and forecast how tumor growth may move. So you can imagine if you want to be able to simulate a tumor that hasn't been treated and see how well your treatment does, and compare and contrast the simulated untreated tumor with what the actual MRI shows, and sort of get an effect of how well that treatment does. Or you can, by using the project that we're doing now, when we're using microglia and trying to simulate their movement, can we actually develop models to model this description between microglia interaction and the tumor, and see what comes out of those kinds of models? Can we recapitulate the same effects in silico as in vivo and compare the differences from there?
What does the math look like? What sort of math do you use?
So for when we're looking at the interaction between microglia and the glioblastoma, we're fitting models of probability distribution functions to these different cell movement patterns. So can we model it via an exponential distribution versus something like a Gaussian distribution, or something a little bit more sophisticated, like fitting a Levy-Flight distribution? And so for that project, it's a much different kind of math than what we use when we are modeling how tumors actually grow and spread through the brain. In that kind of system, we're using a system of partial differential equations. And all this is basically done using MATLAB.
Anything else you wanted to cover?
I think I would say for the audience that's really interested in wondering whether they want to actually incorporate math into biology or continue their studies in math if they're thinking about being in biology, I would say it's an extremely advantageous tool to use to learn and to give it a try, give it a shot beyond the calculus level, because after calculus you're really getting into some amazing math. And I don't mean to diminish the beauty and wonder of calculus, because it's just a fascinating area of study. But when you're able to employ the tools that calculus was meant for in the first place, it's just amazing, and it's just so fun to be able to work with.